Now we want to start expanding out our view of what weak acids are and talk about dissociation constants. So we previously said that strong acids completely react with water. So all strong acids, you can use stoichiometry to determine the concentration of hydroniums in the solution. And as a result, all strong acids with the same concentration, we would expect to have the same pH because they all behave the same way in water. It's all the same stoichiometry. It's one transfer of an H+ to the water to produce an amount of hydroniums. So for a given concentration of a strong acid solution, it doesn't matter what the strong acid is. This sort of, we can kind of replace this replaceability or interchangeability of strong acids is one of the reasons also why we use them in the lab very consistently, because it's just basically at that point in time, just 0.1 molar strong acid solution, they're all the same. But for weak acids, the pH is going to depend on the acid. We know that the pH is, they're all in equilibrium. It's all a reactant favored equilibrium, that reaction with water, and they're all going to have a different equilibrium that is a different pH. So what is the pH going to be for these different acids when they're in water? And that question is going to be answered based on where the equilibrium lies. And so that equilibrium is the reaction of the acid or the base with water. And so we can define an equilibrium constant for that. And when we're talking about these reactions with water, the equilibrium constants are going to have very consistent kind of appearance, where we can have our generic acid, HA. That's a molecule. A is everything else in the acid, and H is the hydrogen part of the acid that you have to have, and it would donate that H, create the conjugate base A-, or just one more negative, and produce hydronium. Because water doesn't show up in the equilibrium constant because it's a liquid, Ka is the equilibrium constant for water, or an acid reacting in water. So K, capital K, is always equilibrium constant. And then this is a type of Kc, because we can see it as the concentrations at equilibrium, but we use a lowercase a to denote that it is an acid reaction. It's the reaction of an acid with water. We can similarly define Kb for any base. B is just our generic base, where it would be reacting with water to produce hydroxide and the conjugate acid of that base. And again, Kb always going to have a similar form. The water, again, doesn't show up, but everything else that is dissolved in water, it does show up in the expression. So we can talk about the Ka reaction for anything that can be an acid, and it will always have this form, this reaction of the acid with water to produce hydronium. Kb is the reaction of the base to produce hydroxide. We call these dissociation constants because it's the idea of, it really comes from this idea that basically the acid here is dissociating, that H is dissociating means fall apart, and so the H is leaving the acid. We thought it just kind of fell apart and floated around. Now we know it goes to the water, but that's kind of historically where this terminology comes from, dissociation constants. So let's get some practice writing out the reactions for these equilibrium constants, these dissociation constants, the Ka or the Kb of HCO3-, which is called bicarbonate. All right, we want the reaction corresponding to the Ka of HCO3-, that's called bicarbonate. And so Ka, the capital K, tells us it's going to be an equilibrium constant, and that A tells us it's going to be the reaction of this as an acid with water. So when we're dealing with K, that's going to be one of our reactants. So it's going to be the HCO3- aqueous. And the other reactant is always going to be water. Whenever you're dealing with Ka, that's what that means. And because it's Ka, what that tells us is that the compound you're looking at, or the substance you're looking at, is going to be the acid, and water is going to be the base. Okay, so that means that, HCO3- is going to donate an H+ to the water. So this is going to function as an acid. We're going to produce the conjugate base of that, will always be one of the products. And then we'd get the conjugate acid of water, which would be H3O+ aqueous. So this is a familiar reaction we've seen before. This is kind of the stereotypical acid reaction in water of the molecule reacting with water, donating a hydrogen, an H+ to the water to create hydroniums. So when we're talking about Ka, that is just always going to be the reaction we're talking about. So we can just say Ka of whatever the molecule is, and we know the other reactant will always be water. You'll always make the conjugate base of that, and then hydroniums. So you know whenever you're dealing with Ka, one of the reactants is water, and one of the products is always going to be hydronium. And then you're told you have to know what the other reactant is, the acid in the reaction. Then you can predict the product of that based off conjugate pairs. So then we can similarly define Kb, where it's the same idea, but instead of behaving as an acid, the molecule you specify, HCO3 minus in this case, is going to behave as the base. So the HCO3 minus is going to be the base, and H2O is going to be the acid. And so if this thing is a base, it would be accepting an H plus from the hydronium. You get H2CO3 aqueous plus hydroxide. So this is, again, just like this was the kind of stereotypical acid reaction in water. This is the stereotypical base reaction in water, where that molecule is reacting with water, taking away an H plus from the water to produce hydroxide. And so this is kind of the stereotypical reactions that we can deal with. And again, you'll note Ka, it's water becomes hydronium. Kb, water becomes hydroxide. And you can specify whatever it is. You'll note HCO3 minus is amphoteric. It can do either type of reactivity with water. So you can define a reaction for both. Things that cannot be acids can't have a Ka. But this is just, we're saying this is the reaction that could happen. We're not saying this will or it'll happen a lot, just that both these reactions could happen. We can always define what the reaction is whenever we see that Ka or Kb. Defining these dissociation constants Ka also lets us distinguish between strong and weak acids. So we've already said strong acids, when they react with water, go to products. That means the equilibrium constant, the Ka, is greater than 1. So it's a product-favored equilibrium, and weak acids are distinguished by having a Ka that is less than 1. So this would be a reactant-favored equilibrium. That's the same thing as saying the reactants mostly just stay reactants. You don't make a lot of products. Less product will be produced than the amount of reactant you start with. In this case, the acid you put in, not all of it becomes hydronium. So that hydronium concentration will be smaller than the initial concentration of acid that you created. Within our weak acids, so we can look at tables of Kas. You can look them up. Here's a nice table that we have of a sampling of weak acids. These tables can be huge. There are tons and tons of weak acids, right? It's just all the not strong acids. And they have varying values of Ka. And so within weak acids, not all of them are going to be created the same. There are variable levels of Ka. And the higher the value of Ka is, the stronger the weak acid is. These are all still weak, but we can see something like iodic, where Ka is 1.6 times 10 to the negative 1, or 0.16, is going to be a much better acid than something like hydrogen peroxide, where the Ka is 2.4 times 10 to the negative 12. So that's a really small value for Ka. Hydrogen peroxide really is not going to affect the pH much. Iodic acid up at the top, it won't affect the pH as much as a strong acid would, but it will still have a larger effect on the pH. And so the relative strength of weak acids is directly related to the value of Ka. These relative Ka values then can inform what the strongest acid is. So if I look at, say, HNO2, HCN, and H3PO4, if I want to know what the strongest acid is, I can just look up the Ka values. These tables are generally arranged numerically. So H3PO4, highest up on the list, 10 to the negative 3rd, HNO2, 10 to the negative 4th, and HCN near the bottom, 10 to the negative 10th. So what that tells me is that H3PO4 is the strongest of these. They are all still weak acids, But what that means is if I have the same concentration of all of these three acids, I would expect H3PO4 to have the lowest pH because H3PO4 is the strongest. It has the greatest effect on the pH. It will produce the most hydroniums of these. It won't necessarily make a lot of hydroniums. It is still a weak acid, but it will certainly make more than HNO2 and it'll make way more than HCN down at 10 to the negative 10th. So you can get a relative ordering of strength here. So if we're looking at weak acids, if we have different weak acids that are all at the same concentration, we expect them to all have different pHs. And whichever of those weak acids is the strongest will have the lowest pH because it would have the greatest effect on the pH. You're making the most hydroniums. So we can see then that, H3PO4 has the largest Ka, it has the lowest pH. HNO2 is the medium, kind of middle of these two. It has the middle pH. And we can see that HCN has the lowest Ka and then the highest pH. And so when we're looking at this, we can see that sort of relative positioning here. We can also see that these are kind of close. These are 10 to the negative 3, 10 to the negative 4th. The pHs are close. This is really distinct, 10 to the negative 10th, and its pH is all the way at 5. Right? That's not that different from pure water at 7, but it is still different than pure water. It's just not pushing as much. HCN is a pretty weak acid, and H3PO4 is pretty decent as far as weak acids go. You'll also even note the strong acids are only at pH 1. 1.6 isn't that bad. It is a pretty good, pretty strong weak acid. It is a stronger weak acid, right? It's kind of relative, stronger, weaker within the realm of weak acids. So we still kind of want to focus on this qualitative ordering. We want to be able to look at solutions and make predictions of what the relative pH will be. We're not predicting pHs yet of weak acid solutions, but just if I have 0.1 molar of all these different solutions, what would the pH, what would we expect to have the lowest pH all the way to the highest pH? That qualitative ordering we want to be able to come up with. Okay. So we want to arrange solutions by pH from lowest to highest. All right, so if we want to remember, what does relative pH mean? So lowest, low pH, we're looking for acids. High pH, we're looking for bases. So when we look at all of our solutions, one of the things we can note is that in all of them, it's the exact same concentration. So they're all at the same concentration. So the question would be, which ones are acids, bases, strong bases? And so one of the things we can focus in on is just looking at if I have my H's, those all have H in the front. Those are all going to be acids. Because I have these hydroxides, we know that that's going to be a base. And then NH3, because it has that nitrogen, that's also going to be a base. Okay, so we can already think right away, acids are going to have a lower, acids are going to have a lower pH than the bases. So we can kind of plot out our kind of trajectory that we would expect. We're going to start with low pH and go to high pH over here. And we know overall it's going to be the acids on this side because acids decrease the pH of water. And it's going to be base on this side. And so we could kind of already take that grouping. We know acids, lower pH relative to the, say, water, and then bases raise the pH. And in general, we know that the relative ordering is going to be that because these are all the same concentration, we know that we would expect the weak to not do much, right? Weak things do not affect, this should be weak acid. Weak acids and bases don't affect the pH as much as strong bases and strong acids. And so this is going to be, because they're all the same concentration. The point in time when they're all the same concentration, all that's going to matter is relative strength. The strong will have, will move the solution pH more. So one of the things that we want to look at is we already identified each of our substances. We can classify acids and bases. So the question is, which ones are going to be strong and which ones are going to be weak? if we look at our acid list, we have HCN, HF, HCl. Identifying strong acids is just looking at the list of the 6 strong acids. HCl is on there. That's strong. HF and HCN are not on the list, so those are weak. When I'm looking at bases, Na and K are in the first column on the periodic table. They are paired with hydroxide here, so that is going to be strong. A nitrogen base is going to be weak. So with this ordering, I can already, with that designation, I can already start to do some ordering. Weak base right here, I only have one of those. So this is going to be my NH3 solution. Strong acid, I only have one of those. The lowest pH is going to be my HCl solution. So I have 2 weak acids. I'll need to figure out how to distinguish those. And I have 2 strong bases. We can classify those. So we'll start with the strong bases. So 0.1 molar NaOH, 0.1 molar KOH. The thing about strong bases is that those reactions go to completion. What that means is that they just, all of the 0.1 moles that of the sodium hydroxide you put in there dissolves and becomes hydroxide. You get hydroxide anions. Same thing with the potassium hydroxide. So one of the reasons why we can use strong base is that they are identical. So the NaOH will be equal to the KOH. If you have the same concentration of strong base, you would have the exact same pH. The same thing would apply for strong acids. 2 different strong acid solutions with the same concentration. So for example, HCl and HNO3 would both have the same pH because they're just reacting by stoichiometry, and the stoichiometry of these strong acids and strong bases with water is always the same. It's always 1 mole of strong acid reacts with 1 mole of water to produce hydroniums, or 1 mole of these dissolve because they're soluble. So strong acids and strong bases, they have the same concentration. They have the exact same pH. So strong acids are the lowest, strong bases are the highest, weak base and weak acid is in the middle. And we have 2 weak acids here that we want to distinguish. So they are both weak acids, but when it comes to weak acids, there is variable strength. For strong acids, they're just strong. They would all have the same pH. But weak acids are going to be variable. And how we can figure out the relative strength is by looking at the value of their Kas. So I have HCN down here and HF right here. And this table is arranged. You can see the Ka is getting smaller. That exponent is getting more and more negative. So HF is 7.2 times 10 to the negative 4. HCN is 6.17 times 10 to the negative 10th. This value is lower than this value. HF is a weak acid, but it is stronger than HCN based off the size of Ka. When HF reacts with water, more hydroniums will be produced than when HCN reacts with water. So we can see that the relative ordering on this would be you'd have HF and then HCN, because here the Ka of HF was 7.2 times 10 to the negative 4. A little line there. And for HCN, Ka was equal to 6.17 times 10 to the negative 10. And so because this number, negative 4, is less negative than negative 10, HF is a stronger acid than HCN. So HCl, Ka is greater than 1, so that's why it's the highest, right? That's why it is a strong acid in that case, and so we can see Ka would be the biggest there, then HF, then HCN. And so HCl as a strong acid is the most effective at affecting the pH, or changing the pH. HF is not as good at HCl. It's not good in general, but it's better than HCN, so you would get a lower pH in there. And so for strong acids, same concentration would give you the exact same pH, but for weak acids, that is not the case. They will have variable pHs.
Participation 227, question 1. Arrange the following solutions by pH from lowest to highest. They're all 0.1 molar, and it's HCl, HClO, HClO2, and HClO4. This is the first question on participation 227, due Friday, February 27th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, arrange the following solutions by pH from lowest to highest. It's 4 solutions. They're all 0.1 molarity. It's hydrochloric acid, hypochlorous acid, chlorous acid, and perchloric acid. Okay, second video done. First question for participation 227 has been found, though. Plenty more videos to go. Looking for more questions. See you in the next one.